Hello, everybody. So today we're starting to discuss time complexity in our investigation of the efficiency of computations, what can and cannot be computed efficiently. And we're starting by discussing efficiency in terms of time, the time it takes to compute whatever we want to compute. By the end of this class, this picture down here would be so familiar to you, and you would be able to describe it in your sleep, even dream about it, who knows. So computational complexity theory asks about what can and can't be computed with limited resources. So it's not enough just to say what can be computed in principle. If we have all the time in the world and all the memory in the world and all the other resources, and perhaps to show that something can be computed, but in time that is longer than the time since the Big Bang, and with memory that's larger than the number of atoms in the universe. This is not efficient. So we ask about efficiency, and we'll concentrate here about time. We'll talk a little bit about space. We'll talk even less about randomness. We talked a little bit about communication. There are other notions that we won't even discuss, like power, which is very relevant when we're talking about mobile devices. So there's lots of things we want to ask in terms of the efficiency of resources that we are going to use. And the theory is trying to capture many issues in practical problem solving, because we do want to answer all of these questions. And we want tools that will be robust enough so we can apply them even when technology changes. The field is very rich with problems that are very important, and many are way beyond our current understanding. On the other hand, we do see progress all the time. And I'm teaching this course and other teaching subsequent courses to try to elicit you joining us in the attempt of solving more and more of these important open problems. And as I said, we'll start with time complexity. So measuring the time complexity of a Turing machine, we just measure it by the number of steps it takes the Turing machine to halt. Right? Every step you're applying this transition function, and we just count how many times you applied the transition function, how many transitions you took, how many steps. We'll give an example. We'll need a little bit of analysis of the time complexity of algorithms, definitely nowhere in the level that you will experience in CS161, all very, very basic. So let's consider as an example the language 0 to the k, 1 to the k, which we know is not regular. And so we cannot compute it in time. We cannot compute it with a DFA. But we can compute it with a Turing machine, and here is a possible Turing machine that computes it in terms of its pseudocode. So one, scan across the tape and reject if the string is not of the form 0 to the I, 1 to the j, meaning the input is not starting with 0. At the moment we see the first one, it has only ones going forward. Then we can immediately reject. This is a simple operation. Then we're going to repeat the following until, or as long as there are both zeros and ones on the tape. We're going to scan across the tape, crossing off a single 0 and a single 1. And if there is a 0 remaining after all the ones have been crossed off, or vice versa, you're going to reject. But if you, when you erase the last zero, you also erase the last one, you know that there were the same number of zeros and ones. So it's not very hard to convince ourselves that this algorithm is correct. It does accept exactly strings of the form 0 to the k, 1 to the k, and nothing else. And now we'll ask, what is the time complexity? So the first step takes order of n. Just n operations. It's just one scan, and you're doing something very minimal at every step. This could have been done by a DFA. So you scan and go back, for example. Then the next step will take n squared. Because it is composed of n or omega n number of iterations, or at least in the worst case, if your input is of the form 0 to the I, 1 to the j, the number of iterations is the same as the minimal of the two, because then that's when you realize that either I equals j or I is different than j. But this could be as high as n over 2. So the number of rounds can be as high as n over 2, which is omega n. In each one of these rounds, you scan the tape to go from the zeros to the ones, across perhaps other elements that you already crossed off. And so each one of these iterations takes order n, and in fact also omega n. So this is order n squared. And finally, just verifying the last thing is still order n. So for example, verifying that you're left with nothing on the tape will take order n. So in total, the number of steps you're taking is order n. That's just an example of counting the time complexity of a particular computation. So let's define things a bit more formally. Let M be a Turing machine that halts on all inputs. So again, to emphasize, forget about undecidable languages, unrecognizable languages, anything higher in the hierarchy of computability. We don't care about it anymore. Now we're only in decidable languages. So these are things that can be computed, but we're asking how efficiently. And the definition that we're going to have is that the running time, or the time complexity of a machine M, is a function that is a function from the natural numbers to the natural numbers, from the input length to the time the machine takes on inputs of this length. And T of n is the maximum number of steps taken by M over any input of length n. So this means that if the time complexity of T of n, the machine M will never take more than T of n steps on any input of length n. This is the worst case aspect of this definition. This is worst case complexity. We're measuring the behavior of M on the worst input, the input that makes it run the longest. There are, of course, a lot of interesting things beyond worst case. Perhaps I'll hint about it at the end, but this is beyond the scope of this class. So now we know how to analyze the complexity of a single Turing machine on a language. But what about the complexity, the inherent complexity of the language itself? In general, in complexity theory, we try to classify the problems by their inherent hardness. So we say all of these problems are in the same class because they require the same amount of resources. So we need to talk about what a problem requires. So let's define it. The time t of n for some function t is all the languages L prime such that there exists some Turing machine with time complexity order T of n so that L prime equals L of m. So there is some Turing machine that computes this language, that accepts this, that decides this language with in time T of n, or order of T of n. So this is kind of the best case. So we want the best algorithm. We measure the complexity of algorithm based on their worst input, and we measure the complexity of the language based on the best algorithm for this language. Of course, there's always, it wouldn't make any sense to do otherwise, because there's always horrible computations for every language. I can just sit and waste time and do whatever I want, and at the end, spit the answer. So wasting time is not difficult. We all know it. That's what Facebook and Netflix are for. And so we want the one that is the most efficient. So in a different way, L time T of n are all the languages that are decided by a Turing machine with order of T of n running time. So what we showed before is that A, this language of 0 to the k, 1 to the k, is in time n squared, because there is some algorithm that computes it in order n of squared time. Perhaps it's also can be computed in a smaller amount of time, not perhaps, we'll show it very soon, but it's still also in time n squared. It's also in time n to the 4. But the interesting statement is putting it in time that is as small as possible. So now we'll show that, in fact, this language is in time n log n, so better than n squared. And here is kind of a condensed version of its pseudocode. First, you again check that it's of the form 0 star 1 star, otherwise you reject. This is order n time. And now you repeat until all the bits of W are crossed out. First, you check if the parity of zeros and parity of ones is the same. If they are the same number, they also have the same parity. If either both of them are even or both of them are odd. If they're not, you can reject. This is something that takes order n to check. Again, this is something that a DFA can do. Whatever a DFA can do can be done in order n. A DFA just runs order n. And now you cross out, after you verified it, you cross out every other 0 and every other 1. So you're going to, let's say the parity was even for both, you're going to divide the zeros by half and divide the 1 by half. And if it's odd, then it's dividing, it's the ceiling of dividing by half. Now, now if the number of zeros is equal to the number of ones, then this operation will, of course, keep the number of zeros and ones the same. If the number of zeros is different, then this operation will keep it different. And this operation also progressed much more quickly than in the previous algorithm when we crossed off one at a time. So crossing off one at a time is much less efficient. So here, instead of n steps, we're going to do just log n steps. And once all the bits are crossed out, we're going to accept. So as an example, if this is the example, we are going to cross off every second 0, every second 1. We're going to cross off every second 0 again of the remaining, every second 1 of the remaining. every second zero of the remaining, every second one. In each of these operations, we had the same parity. We had the same parity from the start, and we kept on having the same parity. And now we crossed off everything, and we can deduce that that we had the same number of zeros and ones, and accept. So what did we see? We seen that sometimes the most obvious algorithm is not the most efficient one. There are, of course, much more interesting examples of that. CS161 would show you many of these examples. My favorite is long multiplication, something that we learned from young age that it takes n squared, and it turns out that it takes much closer to n. So instead of being much less efficient than long addition, it's actually very similar. So that's one thing we saw, that just giving a natural algorithm and analyzing its complexity doesn't tell you the complexity of the problem. There could be more efficient problems. There can be more efficient computations. And we learn a few more things from this example soon. So it can be proved that a one-tape Turing machine can decide A in less than order n log n time. And why is it so? It turns out that that for every f of n, which is a little bit smaller than n log n, so that is little o of n log n, put differently, it is n log n over some alpha n, which alpha n is unbounded. It's going to infinity as slowly as you want. Then time f of n contains only regular languages. And regular language can also be computed in linear time. So what did we learn out of it? Well, first we know that the problem we looked at A is not regular, so it cannot be done in less than n log n. So we identified for this problem the exact complexity for one-tape Turing machines. We saw, therefore, that more time in this example give you more power. So in n log n, you can already do things that you cannot do in n. That's one thing. But we also saw that not every bit of power is useful. Every bit of more time is useful. So if you have, for example, time n log n, you cannot do anything that is not regular. So times n log n is the same as time n. So in this example, a little bit more power doesn't break you from regular languages, but logarithmic more time gives you more power. I'll say it again because I kind of confused it. A little bit more time doesn't help you get more power. You're still only computing regular languages. And logarithmic more time does give you more power. You can compute non-regular languages. There's still one more thing that I want to tell you based on this example. And that is that two tapes can be more efficient. So we know a problem that on one tape requires n log n time. And this problem can be decided on two tapes in time which is order n. And the proof idea is just to scan all the zeros, copy them to the second tape, and then scan the ones, and then one by one go, and for every one, erase a zero, and see if you get till the end the same time. So that's an easy algorithm, takes order n in two tapes. So this also tells us that different models of computation can yield different running times. So an amazingly strong church Turing thesis is not correct. Different models don't imply exactly the same time, but hopefully they don't make a huge difference. So n log n is to n is the example we saw. In fact, you can look at a different language, B, which are all the WWs, with the W is in 0, 1 star. The gap here is quadratic with two tapes. You can still do it in a linear time, and with a single tape, it requires quadratic amount of time. And actually, you have enough knowledge at this point to actually prove it. I probably won't make you, but you do. So we saw that there is a difference between two models of computations. One is a Turing machine, one is a two-tape Turing machine, or we can also think about a constant number of tapes Turing machines. And it turns out that this difference, and we saw actually, we didn't prove it, we saw an example with quadratic difference. And in fact, this is the worst possible difference. So now we see that the picture is not ideal, but it's not the worst it can be. So here is a theorem. For any t that is not too small, t of n is larger than n for all n, and every tn time multi-tape Turing machine has an equivalent order of t of n squared time one-tape Turing machine. In fact, we are just going to see the simulation of a multi-tape with a single tape, and to count it a bit more carefully and see that the exact simulation we already saw already gives this theorem. So our simulation already achieves it. And a corollary is that suppose A can be decided by a multi-tape Turing machine in polynomial number of steps, so some p of n steps for some polynomial p, then A can also be decided by a one-tape Turing machine in a different polynomial number of steps. So in q of n steps for some other polynomial q of n. So this means that there is an equivalence up to polynomial factors. There is an equivalence between these two models. If all we care about is computing in polynomial time, and this is not all we care about, I want to be completely explicit, this is the first order bit that we care about. But if all we care about is computation in polynomial time, then we shouldn't worry about multi-tape and a single tape. And that's great, because who wants to deal with this level of details? So let's briefly remind ourselves of the simulation that we had of multi-tape in a single tape, and kind of let me hand wave that it does what we want. Otherwise, you can look at CIPSR. So we are kind of simulating this step on a single tape. We have all the three tapes written there. And the point is that every step that we have on the multiple tape is simulated by every step on the multi-tape is simulated by the single tape in time which is linear in the length of the combined tape. Because you need to go over, you need to find all the symbols you're looking at, put them into internal memory, decide what are the moves, and implement them. And at times, these implementations would actually mean that you need to kind of spread a little bit all the three tapes to make more room. So like in this step, once we get to the edge of what we had, we needed to push everything away. Every one of these things can be done in time which is linear in the size of this tape, in the size of the single tape that captures all three tapes. So how much time does this mean? I want to claim that if this is order t time, then this is order t squared time. And the number of steps we're going to simulate is t of n time. And now I need to claim that each one of these takes order t of n time to simulate. For that, we need this simple observation that in time t of n, the heads on each one of these tapes can only get as far as t of n steps away. So the length of this tape that combines all of them is of size at most 3t of n plus these additional separators. So 3t of n plus 1, order of t of n. And as I said, each step is simulated in order of this length time. So altogether, every step is simulated in time order of t of n. Not very important. You can also convince yourself or read it, but that proves the theorem. So what do we have so far? We do have that different models have some difference in time. In particular, multi-tape versus single tape can have up to quadratic difference in time. But yeah, they can have this difference, and this is the worst that they can have. We've seen also that in particular examples, let's say for a single tape, a little bit more time gives you more power, doesn't give you more power. Between n and n log n doesn't give you more power, but between n and log n, you do get more power. And now we want to kind of formalize this notion that more time is more power by this notion of a time hierarchy. And for that, we will need to revisit, in this part of the class, we are revisiting many of our old friends from the previous chapter, but with a little bit more attention to details, more attention to efficiency. So we'll discuss an efficient version of a universal Turing machine. So the theorem, there is a one-tape Turing machine U, which takes as input the code of an arbitrary Turing machine M, an input string W, this is what we had before, but also a string T, a string of T1s, where we want the T to be larger than the input. We don't want to discuss any simulation in time that is sublinear. It doesn't make much sense for a Turing machine. It does make a lot of sense for other models, which I don't know if we'll discuss. Well, actually, we will discuss one example. But for now, we have the machine M, the string W, and T, a string of T1s that represent the time we want this simulation to run, and the time is larger than the length of W. And what this machine does, like the previous universal Turing machine, is simulate the run of M on W, but essentially it tries to simulate this run for T steps. It simulates the run of M on W in T steps. So U accepts M W 1 to the T if and only if M accepts W in T steps. How much time does U itself take to run? It takes to run order of the size of M, size of the description of M squared times T squared steps. So M would take T steps to run. If we, let's say just now that we ignore this other factor of the size of M squared, then we're going to run in time quadratic in this, so in time T squared. And in fact, the simulation will have to look at this machine M many times. So it will be actually the size of m squared times t squared. So this is a universal Turing machine with a clock. We're simulating m on w, but we have a clock that keeps on ticking t times, and then we stop the simulation. So this will not run forever. The idea is to first do it in a multi-tape fashion, and then use the reduction from multi-tape to a single tape. So we can have such a U in a multi-tape that only takes the size, the length of m times t steps. So you put the description of m on one tape, the input on the other, and now whenever you want to simulate one step of this machine, you need to scan the tape that contains m for the right transition, and once you find the right transition, a transition that is consistent with what you see at the moment, you're going to execute this transition on the first tape. And you also need to run on m to verify if your new state is an accept or reject, then you're going to halt. And in addition, you also have another tape that contains these T1s, for example. And every time you complete simulating a single step of the original Turing machine of M, you're going to cross off one of the ones. So either you accept because before you already accepted or rejected, either you halt because you already accepted or rejected, or because you crossed off all the ones and then you just halt. And with this more powerful or more refined notion of universal Turing machine, we're going to discuss the time hierarchy theorem. Slightly confusing. The details are important to some extent, but not completely. Again, something that Zipser would do with more details. And the intuition is if you get more time to compute, then you solve strictly more problems. Definitely you don't lose power. You don't get into a situation where you cannot solve something, but you can, in fact, solve more problems. So the theorem is that for every reasonable f and g, which are two functions that will be representing to us time complexity, and for all n, as long as g of n, so if for all n, g of n is larger than n squared f of n squared, then the time f of n is strictly contained in time g of n. So in time which is larger than n squared times your original time f of n squared, you get more power. You get to problems, you get a class which is strictly larger. Now I still owe you some explanation of what these reasonable functions f and g are. I will not fully define it, but essentially this is what's known as constructible functions. At some point we'll need to kind of compute this function, especially f, and we want to be able to compute f of n in time that's not much larger than n. Every function we care about, definitely every function that's larger than linear that we care about, will be in this class. So if we talk about n squared, n cubed, n log n, all of this will be okay. The proof idea is to do diagonalization like we proved for ATM, but now we're doing diagonalization with the clock. So previously, if you remember the diagonalization argument, we had this matrix, we have machines here and inputs here. And now we're going to talk about machines here, not all machines, but all machines that run in time f of n. How can we make sure that all of our machines run only in time f of n? We'll make sure because we will run an arbitrary machine. We will actually enumerate all machines, but we will add to them a clock. So these machines, we're going to cut them off after f of n steps. To do that, we need f to be reasonable. So what do? We take we make a Turing machine n that on input m, another machine, simulate the Turing machine m on itself, on an input which is the encoding of m. Whenever I say m on itself, what I mean m on its encoding, for f of its encoding length steps, and then flips the answer. What we'll see is that if f is, for every problem that can be computed in time at most f of n, stopping it after f of n steps doesn't matter. So this is what I mentioned in terms of enumerating things and just stopping them. But what we can see is that this machine n by itself computes a function that cannot be computed in time f of n. Otherwise, it will be a row in this matrix, and then we'll have a problem with the diagonal. So we won't draw this picture. Instead, we'll prove it directly. So what we'll prove is that while n can be executed in time, which is n squared f of n squared, because of the universal Turing machine, it computes something that cannot be computed by any time g of n machine. So, right, so L of n will not have complexity f of n, but it will have complexity g of n. A little bit more details. We define the machine n as we said before, n on the machine m as input computes t, which is f of m, f of the length of the description m, so f of its input length. For that, we need, for this to be efficient, we need this notion that f is reasonable. And it runs the universal Turing machine with a clock on m, its own description as input, and the clock 1 to the t, and outputs the opposite answer. The claim that L of n does not have time complexity f of n, and the proof is that is on by contradiction. Let's assume that n prime runs in time f of n and actually compute the same language. So assume that there is some n prime that computes the same language as n, but in time f of n. Then this will be the row that will actually create a contradiction, the row in this matrix. So by assumption, n prime on n prime runs in time f of n prime and outputs the opposite answer, the opposite output to what u on n prime, and one of this number of steps do, right? Because this is what n does. N was defined to do that, and n prime does the same thing, and that's what they do. They compute with the clock, and then they switch. But by definition, the universal Turing machine on n prime, and this number of steps, except if and only if n prime on n prime accepts in this number of steps. And this is a contradiction. On one hand, it's going to do the opposite. On the other hand, it's going to do the same thing. This is very, very similar to the proof that ATM is not decidable. What's left to, so now we say that L of n does not have time complexity f of n. What's remain to do is to say that it does have complexity g of n, and this will be the separation. This would actually have all the ingredients. This is a simpler part. So what does it do? It computes f of m, it runs the universal Turing machine, and it outputs the opposite. So computing f of m in an order of g of m time is easy, and this is a very weak notion of being reasonable. Simulating u of m, m1 to the t in an order of g of m time, this is just what the universal Turing machine with the clock do. This is the theorem we had. U of m w1 to the t halts in order of m squared t squared steps. And if we and the way we set g is such that the requirement from g is such that this is less than g of n. And finally, of course, flipping the outcome is order 1. So with this, we prove the entire hierarchy theorem. I want to say that, right, and another remark is that time hierarchy also holds for multiple Turing machines. So it's not that once you go to multiple Turing machines, then more time is for free. In fact, this is not the best time hierarchy theorem, but I do believe that Zipser does discuss more tighter time hierarchy theorems if you're interested, but it's just good to know. So for reasonable f and g, where g of n is just larger than f of n log squared of f of n, so quasi-linear in f of n, time of f of n is strictly contained in time g of n. The corollary is that time n is strictly contained in time n squared, strictly contained in time n cubed, and so forth. So there is an infinite hierarchy of increasingly more time-consuming problems. And one interesting question that we don't have an answer to is, are there important everyday problems that are high up in this time hierarchy and cannot be brought down? In fact, all the examples we had, even for very complicated algorithms, we started with just proving as a first step that there is some polynomial time algorithm, and usually we brought it down to a much smaller coefficient. So you don't stay with the n to the 40 algorithms for interesting problems. There are problems, we just proved it, but so far it didn't create much harm to us. So is there a natural problem that needs exactly n to the 10 time, meaning not smaller than n to the 10? This is open, it's very interesting. But it also kind of suggests this notion of polynomial time, which is the union of time n to the k for every k in n. So every problem that can be solved by some Turing machine that runs in some polynomial time is in P. And in some sense, we want to call it efficient. There is an entire debate about it. Yes, people would tell you n to the 100 is not efficient, or even 2 to the 100 times n, which is linear, is still not efficient. It's not that we don't know all of it. We know all of it. But this has been a very, very useful notion that helped us discuss a lot of important questions in their first order bit. There's a lot of interest along the times, and there is a huge enthusiasm due to recent breakthroughs about what's known as fine-grained complexity. So the difference between n cubed and n squared and n squared and n. And there is a lot of work on sublinear algorithms. What can you do in less than n? All of this is very interesting to theoreticians and beyond the scope of this course. And now I want to give you also one variant of the Church-Turing thesis, the extended Church-Turing thesis, which says that everyone's intuitive notion of efficient algorithms is contained in polynomial time Turing machines. So Turing machines can simulate every reasonable model of computation with only polynomial increase in time. If that's correct, then this notion of polynomial time will be completely robust to your definition of efficiency, of the computational model. So efficiency, if it's polynomial time is efficiency, then efficiency for every computational model will be the same. It's definitely true for most things that we've tried, everything for which now there exists some efficient implementation, every programming language that you have, etc. But this one is a little bit more controversial than the Church-Turing thesis. And a potential counterexample is quantum algorithms. For years, we knew that quantum algorithms can factor, at least the particular model of quantum computation can factor large numbers, which we don't know how to do in polynomial time. And we bet a lot of money about not knowing how to do it by standard Turing machines or by any non-quantum or classic computation. This still leaves open the fact that perhaps there is a smarter algorithm that we cannot think of that does factor by standard computations, or that perhaps the model of quantum algorithms is not realistic. It's not a reasonable model of computation. And once we build these quantum machines, we'll see that, for example, we cannot create large enough Turing machines to actually create such a separation. There have been very exciting, very, very recent developments and claims about proving or demonstrating that quantum machines that we can actually build can already do things that we don't expect classical machines to do. This was termed, perhaps unfortunately, quantum supremacy. And since I want this video to stay valid for a few years, I will not get into details because this is such an active area of research that I'll be happy to discuss in class, but I'm betting that every year there will be some progress on this question. Very, very exciting question. But still, the notion of polynomial time, when we think about it as standard computation, is taking us a long way, and I think has a lot of way to still take us. So with that, I will conclude. What we've seen is that more time equals more power, or sufficiently more time equals more power. Different models may differ in polynomial factors, and the extended Church-Turing thesis hypothesized that this is the worst possible, and polynomial time is a robust notion of efficiency. It's robust to different models, definitely to things like how many tapes does your Turing machine have. And what we'll see soon is that it is also robust to reductions. If we want to say that a reduction is interesting between two problems by showing that one problem reduces to the other in some, even very efficiently, even in linear time. And this would somehow, we would like it to imply that if one problem is in polynomial time, then so is the other. We are really using the fact that increasing the polynomial keeps you in the family. So this perhaps meant nothing to you, but it will mean a little bit more when we get to polynomial time mapping reductions. And yeah, all of this can still change when we know that perhaps the language, the class we actually care about is polynomial time quantum computations. But of course, everything that is efficient in polynomial time will stay efficient. It just means that perhaps we're going to gain some more efficient problems, which we should welcome. Thank you.